Good morning, everyone. We're back here, 5 a.m. Regular contest. Assuming we don't completely collapse, we're going to hit the cyan color rank, since that's not too far off rating wise. So hopefully this goes well. And contest begins in 15 seconds. Let BJ be the sum of deliciousness of the toast on the J plate. And the unbalancedness be so we have to make this as small as possible. Okay, I'm suspecting the answer, but I'm not sure if it's actually correct. So, let's see. In this case, we have 3. So these are the number of, D will be the number of double sets that we need. So if we need 4, we have to start at 7. So 0 and 7, 1 and 6, 2 and 5, 3 and 4. It's number of doubled sets. M minus doubled sets. Yeah, if it takes someone 1 minute to solve, I have a feeling this is correct. How many times can the product of all positive divisors of a to the b be divided by a? It's the product of all positive divisors okay, that always seems promising. Do auto refresh here. $300, $500, $700. Maybe this is a case of how many times can it divide into itself with its products. So like you find it for 1. And we can see what the pattern is for 2 and onwards. Okay, if we look at here, we got 1, 2. Okay, if we add in 1 and 16, if we add 16 here, then we're adding in a 4. Well, it's less than C. We have to increase by 1 eventually, but just increment this by B, I think. Yeah, this is pretty obviously wrong. Okay, what the heck have I done here? V1 C mod X 0, then it's a factor of C. Okay, yeah, now we're getting correct setups. Okay, now the question is I just realized this is still completely wrong. If it's a factor, then just Yeah, it takes a while for L to really spiral, so should be okay here. Okay, let's try 6. So we got 1, 6, 2, 3. 2, 9, 24, 50, 2 times 1, 3 times 3, 4 times 6, 5 times 10, 6 times 15. Okay, 6 times 15. 7 times 21. Okay, 7 times 21. Okay, we're already starting to see some sort of pattern going on here. So we got 2 times 1. 3 times 3. 4 times 5, 4 times 6, 5 times 10, 6 times 15, 7 times 21, Let's do another. A equals 2 give 1 times 1. Okay, then what about 4? Let's try 4. 4 is a bit of a weird number. Since you got so 4, 1, you get 1. 4, 2 is 5. 1, 5, 10, 18, 27, 39, Does this work with 9? 9 and 6, 39, as expected, so anything that's like a prime square will exhibit this behavior. Prime numbers will be the triangular numbers. The product of two primes gives this. If we take the multiplication of the two, Okay, don't really see the solution there yet. One, two, four, eight, maybe? Actually, 1, 2, 4, 8 functions like a 2 pair. So then we should but it doesn't. So a cube does something else entirely. Two, 7, 15. Maybe it's, I mean now, okay, it's not, you can't just go to each of the factors and count each one because there's several combinations of the factors you can take to actually to multiply into an A factor. Okay, where are the factors? 1, 2, 3. And then itself. Then why doesn't 6 to the 4th exhibit this behavior? Oh wait, it does. You just add 2 there. And then you add 3. Okay, wait, if we take that part out of the equation, then for this, so 2, 6, 8, 15, 18. Okay, first it's 2, 9, 24, 50, 90, 147. We subtract those intermediate cases, 48. plus 6 plus 18 plus 24, 42, 54. Four, 9, 25. All of those share the same property. What about something with 3 pairs? So like say 2 times 3 times 5. 30. 30 goes into 1, 2, 3. No, not 30 actually. 12. 1, 2, 3. 3 times 4, 2 times 6, and 1 times 12. So 12, 1 starts at 3. Three, 15, 42, 90, 165, 273, 420. I mean, we got 3 times 1, 5 times 3, 7 times 6, 9 times 10. 11 times 15. I think this is 13 times 21. And then 15 times 28. Okay, so... Okay, that's a... All of these are really good clues here. I mean, with 8 we have 1 and 8, 2 and 4. That in theory it should work like 2, but then we get some sort of collision occurring. Because then it jumps into 64. And I'm pretty sure normally that 8 times 8 would have... It would have included this 2. Wait, then subtract 9, subtract 24, subtract 50, subtract 57. That's the answer. Wait, that's actually the answer, isn't it? Okay, what about I mean, with 8 at least that makes some sense. Because you got 2 pairs and you're... Well, I mean, you're holding 2 pairs there, and then you're subtracting 1 backwards. I need some sort of way to figure out if... I mean, I'm not sure how square numbers... How would square numbers by themselves be interacting here? And I mean, technically with 8 it has 2 pairs still. Just unsure how it's interacting with them. If you have 18, what about 36? 36 has 1, 2, 3, 4, 5, and then 6. 6 is a square. We can do a quick A equals 24 check here. Ten times 6, 13 times 10, 16 times 15. $36 is where problems could start. I mean, you still have 4. It's 1, 2, 3, 4. Except now you have a 6. A 6 squared. Four 21, 60, 130, 240. 0, 4, 13. Okay, what can we get from 2, 9, 24, 50, 94, 147 into a square like this? And is there a rule that applies to both of these relationships? Because that's what I'm assuming is going on here. I mean, we may as well try 16 while we're at this, since that's pretty much the epitome of squares all over the place. 1 and 16, 2 and 8. In theory, this should be like a 2.5 setup. Okay, I mean, at this point, we may as well just go. Yeah, I'm using the last ditch effort, which is this. So we obviously know what's going on with some of the cases. What is going on with 1, 5, 10, 18, 27, 39 square cases? It's the expansion of x times 1 plus 3 times x over 1 plus x times 1 minus x to the third. What the hell? Is this absolute value or something? Okay, 3 times all of that. $27, 3 times 3, 10, So we have 30 divided by 4 times... Okay, minus 2 cubed is minus 8. What? Three minus 2 cubed minus 8, 4. Or no, wait, this is the generating function. Okay, yeah, that's probably what's going on here. N squared plus n minus 1 for n minus 1 over 2. Okay, yeah, this is what we're looking for. So 9 plus 3, 12, 11. 11, 3 minus 1 over 2 floored is 10. Yeah, with 4 we can just do a subtract 2 at deck, right? No, not a subtract 2. It's just a subtract 1 still. Take 1, 2, 3, 4, 5, 6, 36, 42, 41, 39. Okay, those line up, so n squared plus n minus 1 Okay, how does 2, 3, 5 actually work? Because you get 1, 2, 3, 5. You have 4 pairs. In theory, this should be the same as 24, but this is done with 3 factors instead of 2. 4. Yeah, this is what I was fearing. So what even is going on here? I mean, at least we probably know it's 77 times 5, 350, 385. Like, if we take 385 and 4, you get 250. So we and this is just 2 times 2 times 1, 3 times 3 times 3, 4 times 4 times 6, 5 times 5 times 10. So the next one would be 6 times 6 times 15, and so on. That's what we can expect out of that. A 3-1 case. Two one. This is 2. This is a 1 case. Two cubed times. We're getting to the point where the numbers are getting dangerously high. 3 times 3 is 9. So this is a 3-2-1 case. Already we have 12, then 105, 420, yeah, we'll stop there. 12, 105, 420. Okay, 2, 7, 15, 26, 40, 57. Those are the second pentagonal numbers. So in this case we got n. Yeah, after that it starts falling apart. Yeah, that's probably the absolute furthest I can reason. $12, $135, $672, 0, 59, 40. So divided by 4, so that's 2. Then a 3, then a 7, then an 11. So it's a 2-1-1-1 setup. What is this? I mean, once you start squaring the number, then it gets It's a bit strange. 12, 1, 6, 7, 2, 2, 2, 4, 8, 5, 9, 40. That would mean we have 12 pairs first, then 767 pairs, then 224 pairs, 562 pairs, 1,188 pairs. Yeah, there's almost no pattern that's actually showing up here. Okay, now that we've shortened the break period, now we just figure out what the hell is going on with this problem. So positive divisors a to the b. I mean, with b we have to have some sort of infinite. Like b can be basically any value, but a can go only up to 10 to the 12. Okay, let's look at the... I mean, if it's 1, it's easy enough. But then after that, it gets a little bit convoluted. 1, 1, 1. We get 3 times 3 times 3. That's 27. If we have a 2, there's a 5. A 2 and a 1, it's a 15. Wait a second. There might be something going on there. A 2 and a 1 and a 1 is 135. If we look here, our 2 is a 5, or 1 is a 3. A 1 and a 1 and a 1 is 135. 2250. We take the fourth value from each of these. We get 10, 10, 10. And an 18. So for some reason this only works on the second value. 3 6s is 216 and a 10. Okay, for only the second value, if you just take the multiplications of every single one, it does work. Why does it work like that is the question I have no idea behind. Yeah, we better look at C and D just in case. I don't feel confident in those two, but I mean, for permutation P, okay, B is quite literally a one-trick math problem, and I'm just here like, what in the heck? What else is there? Maybe it's how many factors first. Let's figure that out. No, wait, then it becomes a massive combination. No, actually we can figure out the number of factors quite easily. The number of factors, you just take its prime factorization of like whatever it is, even like 2, 1, 1, 1. Multiply those numbers by your exponents, so then like by 2 you get 4, 2, 2, 2. And then it's basically a for a 4, you choose 0 to 4, so 5 choices. Then 3 choices, 3 choices, 3 choices, 3 choices. And multiply that together, that's your 405 in that case. That would be the number of factors you have. In those 405 cases, for the 4, you have 81 that are in nil, 81 that are in 1, 81 that are in 2, 81 that are in 3, and 81 that are in 4. Starting to see something here. That would be 810 in total. So it has to be at most 405. 5 there. 0, 1, and 2, you have that divided by 3. Divide by 3, you get 405 divided by 3, 105, 135. For 0, 1, and 2. So yeah, you're still at 405 basically. This is 2, 1, 1, 1, right? Yeah, 2, 1, 1, 1. You square that, you get 4, 2, 2, 2. Oh, I took 4 3s instead. If you take 3 3s, it's 27 times 5. 135. That's it. That's the solution. That might be the solution. I think I figured it out. Okay, we only need... Okay, question number 1. How many primes do we need? We need the primes up to the square root of 10 to the 12. Yeah, that's just a solid 1 million. Okay, let's go. I think I see the answer. I see how this works now. Shit. Okay, why am I logged out of my GitHub account? Algorithms. Okay, we need our prime factoring sieve. We have the number of factors. That's what it was. That feels too easy, but I mean, at this point, you gotta just take what you can get, and at least we're solving the question for once. Sieve up to 1 million. If we get that I times I is greater than A break, if A mod I equals 0, then x equals 0, while A mod I is still equal to 0. Divide by I and add 1, f dot append x. Nine nine 8244353. Okay, first we can test 924.1. Oh shit, we got double the amount. And I forgot to include cases for B. Well, your prime factorization is 4 times 3 times 4 times 3 times 5 times 7 divide 924 divided by 12, 77. Oh wait, this is doing that correctly. Wait, what? How did we only get 12? Are we dividing this by 2? Okay, shit. G times... Okay, one more thing. The modular inverse of this is just this 2 plus 1. Confirm by just doing 299. If it's odd, we have to subtract 1 first. Subtract 1 if answer is odd. Then after that, do this crazy set. Then we're doing the proper 4 division. Sixteen is 2, 2, 2, 2. Okay. Don't need to print F anymore. 2 and 3. Oh, for God's sake, what the fuck? I thought I had it. I thought I had the thing all but dead and done. Do I at least have this here? Not in the slightest. Fricking hell. I had false hope for one moment and then I realized that I have something screwy going on again. Wait a second here. 162, 448, 1125. No, this is 11 times 6 times 6 times 6. 2376 times 5. Wait, that might be what's going on. Wait. This is the fourth value, 1125 times 4. So what happens when every value is odd? Six, three, three. Something like triple ones. You get 2, 2, 2. No, 3, 3. No, all the values are even. Something like 2. You get 4, 5. 5, that's doubled, and then you're going down. 7 times 3, 21. Yeah, okay, if it's an odd value, then we go like this. So if anything in there is... If we ever multiply by something like this, answer mod m, answer times b, eight six seven one. That's the value. That's the code. That is the code. It's like all the answers just crystallized into my brain for once. Come on, please be success. Oh shit. Come on, we have to be somewhere near the answer at least. Okay, we're missing. We're off on some of the cases. We're doing our factorization wrong, aren't we? Is this factorization wrong though? Go 7 times 7 with a bunch of 2's. No, I don't think the factorization is off. I mean, it has to be, I mean, based on what we got, it's... It's number of factors. Our answer has to be at minimum 1. A is at minimum 2. If B is 1, then you have if you have like the number of pairs of okay, wait. I see what we're doing now. We have the number. We're basically counting how many pairs of factors, multiplying that by B because that's how many times it has to divide into A. So that's how many pairs this. If odd, then we have to add in that remaining one for that last factor. The last factor that cannot be paired up. In this case, if it was like 16, it would have to be 4. 4, 2, there. 1, 2, 4, 8, 16. If we're doing a 1 case, then 16 to this mod M. Make sure this still gives the correct answer. There's a difference between this and what we did previously, I'm assuming. Oh, screw it, send it in. Like we started this in the quest for hitting 1400. Now we're going at this for the dignity of at least solving this one problem. I think it goes without saying that this hasn't exactly been one of my better contests. Okay, still the same 15 wrong answers. What are we missing? There has to be something that's going on, but what is it? Oh my god, we aren't including all the... Oh no, no. That is so bad. We aren't including all the primes. Oh no, we aren't including all of the primes. That has to be what's going on. And then it just completely falls off. Come on, please. Please. Okay. No wrong answer. 33, 39, 51, 56. Let's go! Yes! We got B. Screw the rating change, I don't care. I solved B. I always have some of my dignity intact. Hooray. Jesus Christ. That was a... I at least get to say that I solved the second problem. Yep. I looked at C and D. Those problems are an absolute mess. We got 8 minutes left. I'm probably not going to attempt running those down since this took nearly the entire contest for me to figure out. And I think that'll be it. See you Wednesday. And let's hope that the second problem doesn't take me like 1 hour 47 minutes like this one did.